Now, I will explain the energy conservation law. Let's think about an object of mass, m, with an applied force F as a one-dimensional system. We can deform the equation of motion for this system to m minus F equals 0. The left side of this equation is multiplied by the velocity v, and integrated by t. The integration range is from t0 to t. Using the definition of a and v, where a is the time derivative of v, and v is the time derivative of x, we can successfully eliminate dt in the integration. You can then change the variables of integration to v, in the first term, and to x, in the second term. The integration range is also changed from t to v, and from t to x, depending on the variables of integration. We also define the potential energy U, as the indefinite integral of minus F with respect to the position, plus constant like this. You may forget to add a minus sign here, so please be careful. After defining the potential energy in this way, you can substitute the potential energy U, to the integral term of F, in the previous equation. Further calculation yields the integral of the v term in the form of 1 over 2 mv squared. Because the original starting point formula was equals 0, the result is also 0. Now we move the terms at t equals 0 to the right. The sum of the 1 over 2 mv squared and the potential energy, U, is equal to the ones at t equals 0 for arbitrary x. The 1 over 2 mv squared is called kinetic energy. Therefore, we obtain the energy conservation law that the sum of kinetic energy and potential energy is constant. Note that in the special case where the force F is a constant, the potential energy U is expressed as minus Fx plus c. However, in some cases, such as the Coulomb force, the force is not a constant, so it is expressed using the symbol U, defined above as a general formula. This time we did a slightly more complicated task of multiplying the velocity v and integrating with respect t, but when we look at the term for integrating the force, it turns out to be the equivalent of integrating with respect to position x. Thus, the equation for the energy conservation law can be obtained by integrating the equation of motion with respect to the position, and conversely, the equation of motion can be derived by differentiating the equation for the energy conservation law with respect to the position. Generalization of the above discussion into 3 dimensions also leads to the law that the sum of kinetic and potential energies is constant. In the future, quantum chemistry will often use the energy conservation law, rather than the equation of motion, which is the dimension of force, so please remember it. In particular, the terms of potential energy are often used.